We live in the world of big data. Data engineering as a discipline is growing in importance in this regard. How do we do data engineering while building Apache Spark applications? What are the principles and best practices? My name is Kumaran Ponnambalam. In this course, I will show you how to execute data engineering projects with Apache Spark. I will start off by discussing some salient features of Spark that helps in scalable and resilient processing. I will walk through the design of batch and real-time pipelines with Spark using examples. Finally, I will also discuss best practices for building data pipelines. Let's now start solving data engineering problems with Apache Spark. Before we begin the course, I want to discuss the prerequisite skills needed for the students to maximize learning from this course. The focus of this course is to help students build data engineering pipelines with Apache Spark. It will discuss some key design principles and best practices in building pipelines and demonstrate them with examples. The students are expected to be familiar with the basics of Apache Spark and are able to set up, code, and deploy applications with Spark. Familiarity in structured streaming and SQL capabilities for Apache Spark is also desired. The example code is in Java, so familiarity with Java concepts, programming, and Maven builds are required. We will build pipelines using third-party data stores, namely Kafka, MariaDB, and Redis. Familiarity in these data stores is helpful. We will be deploying and using these data stores with Docker, so knowledge of Docker operations is also essential. Let's now get set up with the example code and prerequisites for this course. Let us set up the required software for use in this course. We will use Apache Spark as an embedded service, so we will not be setting up a Spark cluster. We will instead use it directly from IntelliJ IDEA. We, however, need data sources and sinks like MariaDB, Kafka, and Redis for this course. We will set them up using Docker. First, make sure that Docker Desktop is installed and set up on your system. If not, download it from docker.com/product/docker-desktop. Download the exercise files for this course into a local folder on your machine. The folder could be like desktop exercise files. Open the command prompt and navigate to this folder. If you are using Windows, please use the PowerShell application. Now execute the command in Docker Compose to start all the containers. The command is docker-compose -f spark-docker.yml up -d. You should see 4 containers being created and started. This process may take a long time if the images need to be pulled from Docker Hub. We can check the status of the containers using Docker PS. The containers are up and running. Next, install IntelliJ IDEA if it does not exist on your system. Also make sure that Maven is set up and running on your system. Go to the exercise files folder and unzip the project file spark-data-engineering.zip. Now open IntelliJ IDEA. Select Open or Import. Choose the root folder of the project that got extracted and hit Open. This will open the project and download all the relevant dependencies. Again, this may take some time to download. This project uses Java 11. Choose a Java SDK that supports Java 11 or above. To do that, go to the menu, File, Project Structure, Project, and choose a project SDK that's installed on your system. I'm using OpenJDK 14 with the project language level as 11. Hit Apply. Once the Java SDK is selected, the project should download all dependencies and compile cleanly. Now, we need to create a few databases and tables in MariaDB as well as a few topics in Kafka for use in this course. To do this, go to the Setup package and select Setup Prerequisites.java. This class will create all the required elements in MariaDB and Kafka. It creates 3 databases: Warehouse Stock, Global Stock, and Website Stats. It also creates 3 Kafka topics, namely to begin the course, let's discuss the concept of data engineering. Data engineering deals with designing and building systems that collect and analyze data to deliver insights and actions. The focus on data engineering is data, especially big data, and ways to process them at scale and with low latency. Data engineering is a growing field in software engineering, especially around data processing, analytics, and data science. It is driven by the advancements in big data technologies. These technologies enable building data pipelines that focus on data transport, processing, and storage. It is essential for large scale data processing with low latency, which is becoming a key requirement for multiple application domains to deliver value to their customers. It is a prerequisite for machine learning. Large quantities of training data needs to be cleansed, transformed, and processed before they are used for building models. It is also needed for pre-processing and post-processing of data during machine learning inference operations. Data engineering has given rise to a new breed of engineering roles like data engineer and big data. Nowadays, we hear the terms like data engineering, data analytics, and data science when discussing big data. Often, they are used interchangeably. So, what exactly are the differences between these domains and what are their overlaps? This table lists a number of data processing and analytics functions that are encountered in the data analytics domain today. Data engineering deals with the preparation of data for further analytics. It deals with integrating data sources to extract data, build data pipelines for transport, processing, and transforming data to required formats, and aggregations to finally storing them. This data can also be used to build business actions downstream. Business analytics, on the other hand, works on data that is already prepared by data engineering. It deals with using the processed data to create dashboards and reports for doing exploratory data analytics and statistical modeling of data. This includes generating recommendations for business actions. What are the functions of data engineering? Data engineering consists of five functions, namely acquisition, transport, storage, processing, and serving. Data pipelines are built by combining multiple such functions to deliver a given outcome. Let's start with data acquisition. The goal of data acquisition is to extract or receive data from a data source and publish it into a big data pipeline. While acquiring data, the focus is on understanding the format of the source data and converting them into formats suitable for downstream processing. We work with interfaces provided by the source systems to extract data. Alternatively, we can expose interfaces through which clients can publish data into the pipeline. Security is also a major concern, especially if the data sources are not within the trust domain. Reliability of data is of importance, especially when acquiring from remote sources. Finally, latency is also a consideration for streaming data analytics. Data transport deals with moving data within the pipeline to various processing and storage endpoints. Data transport should be reliable and should maintain the integrity of transported data. Transport requires scale to deal with large quantities of data in the big data world. Data security and privacy may also be key concerns. Latency is an important transport consideration for real-time use cases. Finally, transport should also be cost-effective. Then comes data storage. While designing storage for big data pipelines, a key requirement is the flexibility of data, as new use cases and requirements will constantly emerge when the system grows. Schema design needs to consider this. Popular query patterns should be considered while designing the schema. Storage should also provide for high availability and redundancy to ensure resilient operations. Finally, the choice of technology should also be cost effective. Data processing is the next key function. Common requirements like scale, resiliency, latency, and security also apply to data processing. In addition, data processing should provide capabilities for cleansing, filtering, and enriching data with additional features. Data should also be aggregated in cost-effective operations. Machine learning can be part of data processing operations in real-time prediction use cases. Finally, data serving is also an important function. Serving can be done by either exposing APIs and interfaces or by pushing data to endpoints for downstream analytics. In any case, requirements around latency, high availability, and security also need to be considered. Skill levels of consumers should be taken into account while exposing interfaces. The schema of the data should also be flexible to provide for multiple use cases and popular query patterns. When building data pipelines, one of the key decisions to make is whether the pipeline would be batch or real time. We start with batch processing. In batch processing, we process data in batches. A batch is a collection of records with a well-defined size or window. We can either define batch sizes by the count of records or by a date-time range. In batch processing, the batch of input records is already ready and complete. This input does not change when processing is going on. This is a key differentiator between batch and real-time processing. Batch processing works on bounded datasets. The number of records in the batch do not change after the processing has started. Since batch processing usually waits for all the input from that batch to be ready, there is latency when beginning processing. Also, it may take some time to process all the records. The results of processing are usually available at the end of processing, but intermediate results can also be possible. Batch processing is simpler to implement. Since the input is constant, reprocessing would generate the same output all the time. How is real-time processing different? Real-time processing or stream processing works on input data as it is created at the source. It does not wait for the batch of records to build up, rather it processes one record at a time. As processing is going on, the input data may change while processing. Stream processing should account for such changes and reprocess when needed. Change data capture is a key pattern used in these cases. Real-time processing usually works on unbounded datasets. When processing starts, the total number of records to be processed is not known. Processing needs to consider this and compute metrics accordingly. In real-time processing use cases, there are low latency requirements. The insights need to be derived within seconds of receiving the source data records. Not all use cases can qualify for real-time processing. State management becomes an important consideration in real time when entity states or running summaries need to be kept track. Apache Spark is arguably the best processing technology available for data engineering today. In order to build an optimal Spark pipeline, it is important to understand how Spark works internally. When design decisions are made, they need to be analyzed on how they impact scalability and performance. In this video, I will review how Spark executes a pipeline and optimizes it. I recommend further reading on this topic to master the internals of Spark. Spark programs run on a driver node which works with a Spark cluster to execute them. A Spark cluster can consist of multiple executor nodes capable of executing the program in parallel. The level of parallelism and performance achieved is dependent upon how the pipeline is designed. Let's review an example pipeline and how it gets executed. First, the source data is read from an external source database into the structure data1. Data1 is then converted to a data frame or its internal representation, resilient distributed datasets or RDDs. During this conversion, it is partitioned and individual partitions are assigned and moved to the executor nodes that are available. When a transform operation like map or filter is executed, these operations are pushed down to the executors. The executors execute the code locally on their partitions and create new partitions with the result. There is no movement of data between executors. Hence, transforms can be executed in parallel. Next, when an action like reduce or group by is performed, the partitions need to be shuffled and aggregated. This results in movement of data between executors and can create I/O and memory bottlenecks. Finally, when the data is collected back to the driver node, the partitions are merged and sent back to the driver. From here, they are stored into external destination databases. This flow needs to be understood and visualized for any pipeline that we are building to understand bottlenecks and design for scalability. Big data processing is all about processing data in parallel to achieve high throughput in less time. How does Apache Spark help with this goal? Data processing involves multiple activities, which in general can be grouped into the following. First, data is read from data sources like databases. Then, various operations like transformations, data filtering, and validation checks are performed. Data may then be aggregated to create summary metrics. Finally, transformed data is returned to sinks. When we talk about scaling data processing, we need to scale all these steps. We need the ability to parallelize all these steps involved in data processing. Steps that cannot be parallelized become bottlenecks, and the speed of the processing pipeline would be based on how fast these bottlenecks can process data. How does Apache Spark help in parallelizing activities and removing bottlenecks? Let's start with reading data from data sources. Spark supports out-of-the-box parallel read operations from various data sources. Subsets of records can be directly read into multiple executor nodes in parallel. For example, it supports partitioning of data by column values for JDBC sources. Different executors can read and process different subsets of data partitioned based on column values. Similarly, with a Kafka source, each executor can read from a subset of Kafka partitions. It's possible to implement custom parallelism techniques and configure the level of parallelism in Spark. Spark also implements predicate pushdown. Any filtering operations in Spark are instead executed on the data source itself, so unwanted records are not read into memory. This is done by the optimizer while deciding on the execution plan. What about processing of data? Transformation operations like map and filter are parallelized by Spark. Different executor nodes can process transformations in parallel on subsets of data. In order to enable parallelism and reduce bottlenecks, care should be taken during pipeline design. For example, perform map type operations early in the cycle so we can Spark execution plans play an important role in optimizing pipelines. When a job is submitted to Apache Spark, it first analyzes all the code given to it and comes up with an execution plan. Spark has an optimizer that analyzes the steps needed to process data and optimizes for performance and resource utilization. Spark only executes code when an action like reduce or collect is performed. At this point, the optimizer kicks in and analyzes all the previous steps required to achieve this action. It then comes up with a physical execution plan. The optimizer looks for reducing I/O, shuffling, and memory usage. If the data sources can support parallel I/O, then Spark accesses them directly from the executor and parallelizes these operations. This provides improved performance and reduces memory requirements on the driver. It is recommended to print and analyze execution plans to understand what Spark is doing underneath and look for opportunities to optimize them. Please refer to other Spark documentation and courses regarding execution plans. One of the challenges in stream processing is the need to maintain current state for computing aggregations and managing transitions. It is also needed to resume processing after a pipeline is halted. How does Spark help in this regard? Let's start with the feature of checkpointing in Apache Spark. Checkpointing is the ability to save the state of the pipeline to a persistent data store like HDFS or S3. When a job fails and needs to be restarted, the information saved during checkpointing will be used to resume processing from where it left off. Checkpointing will store a number of metadata elements as well as some RDDs at periodic intervals to the checkpoint store. This includes Kafka offsets, so processing can resume from the last processed record. Also, if the state is tracked by keys, then that information can also be checkpointed. Finally, if there are RDDs that require operations like windowing across multiple batches, they will also be stored in the checkpointing process. Watermarks is another important feature of Apache Spark that is useful for event time operations. Event time is the time a specific event or record is created at source. If windowing needs to be done based on event time, then processing of any window may have to wait until all events for that window arrive at the Spark executors. Watermarks are used to set the delay required before processing of an event time window can happen. Spark waits for this delay until all events for that window are expected to arrive. It keeps track of the events and their ordering until the watermark. Analytics and machine learning are two allied domains with data engineering. Apache Spark can also help extend data engineering pipelines to perform analytics and machine learning. Let's start with analytics. Spark supports Spark SQL, a simple yet powerful SQL interface to perform computations and aggregations. SQL is internally translated into distributed operations that can efficiently process large data sets. Spark SQL can be used on both batch and real-time streaming pipelines. Spark SQL syntax mimics standard SQL. It's simple to use and yet powerful to transform, filter, and aggregate data in one single statement. SQL-based analytics can be added to the same Spark pipeline that does data engineering, so implementation and deployment becomes easier. Data pipelines can be cascaded with analytics where the output of one operation can be passed on to downstream operations for further analytics and processing. Results of analytics can either be persisted to databases or sent as streams for downstream consumers. How about machine learning with Spark? Yes, Spark supports ML through a library. Spark ML provides various out-of-the-box features for pre-processing of data. This includes feature extraction, transformation, and dimensionality reduction. Spark provides some popular machine learning algorithms and can support ML pipelines for both training and inference. ML pipelines can be used to stitch data extraction, pre-processing, training. Having discussed the capabilities for Apache Spark in the earlier chapter, let's now design and implement a batch processing pipeline in this chapter. Let's start off with discussing the business use case we are trying to solve with this pipeline. We want to build a pipeline that will do stock aggregation across multiple locations for an enterprise. This enterprise has warehouses across the globe. Warehouses maintain stock of items by location and distribute them to local stores. Each warehouse also has a local data center with all the required hardware and software deployed in that center. A stock management application runs in each warehouse. It is the same software but has local independent instances deployed in the local data center. A local MariaDB database keeps track of warehouse stock information. Stock is maintained by each item for each day. We keep track of the opening stock, receipts, and issues for each item for each day. The enterprise wants to create a consolidated central stock database. Item stock information needs to be collected from across warehouses on a daily basis and then consolidated in a central MariaDB database. We need to set up batch processing to upload local warehouse data into a central data cloud and then aggregate stock across locations. The solution should be scalable to hundreds of warehouses. This is a simple use case but representative of a number of real-life use cases that require data gathering, consolidation, and aggregation. How does the batch data engineering use case design look like? Let's consider three warehouse locations, namely London, New York, and Los Angeles. Each location has a MariaDB database called warehouse stock. There is also a central data center to which the data needs to be uploaded. In order to store the uploaded data in the central data center, we need a file system that is scalable and provides concurrent access. We want to create folders for each warehouse in this file system and provide permissions to the local warehouses to upload their respective files daily. We will choose a distributed file system like HDFS or S3 that provides concurrent access, scaling, and security. Files will also be created in Parquet format that allows for parallel reads by Spark. Now, in each local data center, we will run a stock upload job built with Apache Spark. This job will run on a daily basis on a local Spark cluster. The job will read daily stock information from the warehouse stock database and upload them into the respective warehouse folder. Let's implement the batch processing pipeline we designed in the previous video. The code for this chapter is available in the Chapter 3 package under com.learning.spark data engineering. Before we build the jobs for stock processing, we need to create some sample data in the source database warehouse stock. We will do so using the raw stock generator.java class. The generator generates data for three warehouses, namely New York, Los Angeles, and London. In real life, these will be three separate database instances, but for this example, we will create all the data in the same database. The generate data method is called once for each of these warehouses. This method uses a simulated list of items and their values. It also uses a random number generator to generate stock counts. It generates stock information for 3 days starting from the 1st of June. We first connect to the MariaDB instance of warehouse stock and create a prepared statement for these inserts. We then iterate for 3 days. For each item in the list of items, we pick random values for the opening stock, receipts, We will build the daily stock upload job in this video. The code for this job is available in daily stock uploader job.java. If you are using Windows, make sure to download the Hadoop binaries into a local directory and set up the hadoop.home.dir system property to point to that directory. The upload stock method is used to upload stock for a given warehouse and a time period. Multiple copies of the job are expected to run, one each for each of the local data centers. We will, however, run all of them together in this example for demo purposes. In the job, we first create a SQL query to find the minimum and maximum values of the ID column for the given date range and warehouse ID. The ID is an auto-generated column populated in the source database when new records are inserted. We will use this column to partition database reads across multiple Spark executors. The minimum and maximum values are captured and stored in the min bounds and max bounds variables. Next, we create a Spark session. We use the local of 2 to run the embedded version with 2 task nodes. The default parallelism is also set to 2. While running in a cluster, this can be fine-tuned based on scale requirements. Now, we set up the query to get stock information for a given date range and warehouse ID. We execute this query and read the results into a datasets. While reading, we provide various database connection parameters like URL, DB table, user, and password. In order to use partitioning, we convert the query into a temporary table and provide that to a DB table option. In order to enable parallelism, we need to provide the partition column and the upper and lower bounds. The num partition is usually equal to the number of available executors. This will enable reading and uploading of data in parallel across multiple executors and enable scaling for the job. We are not going to use S3 or HDFS as the central file store for this example. Instead, we are going to use the local file store created under the raw data directory under the project folder. Please delete this raw folder if it already exists. Otherwise, it may generate an error. For using S3 or HDFS, simply provide the corresponding URL in the path provided. The file will be created in Parquet format. We will also partition this data by stock date and partition ID. This will help in querying data later if filters need to be applied based on these attributes. Finally, let us aggregate the stock information we collected across warehouses in this video. The aggregate stock method will summarize stock values for all records available in the source directory provided. The source directory is raw data that we populated in the previous video. We first create a Spark session for the Spark aggregator job. We read the source directory in Parquet format and create a dataset. We then print the schema for the dataset to make sure that the data has been correctly read. Next, we create a view on the dataset. Creating a view enables us to directly run SQL statements against the table. It makes it easier to do computations and queries this way. We run a count star query and display the number of records in this table for checking purposes. Next, we run a group by query for summarizing stock across warehouses. It groups data by stock date and item name. It adds up the opening stock, receipts, and issues. It also computes the closing stock and the value of that stock. The results are stored in the stock summary dataset. Now, we will write these results to the item stock table in the global stock database. Spark allows out-of-the-box capabilities to append data to a JDBC table. Do note that we are using MySQL in the URL instead of MariaDB since there could be potential issues by using MariaDB in the URL. The functionality is the same whether the target database is MySQL or MariaDB. Let's run this code and review the results. The job has been successfully executed. It has printed the schema, the total number of records available, and the stock summary that has been posted to the database. We can also review the counts of the global stock database that has been created using the global stock db browser.java class. Let's run the browser and review the counts in the table. We can see the number of records. What will a real-time data engineering solution be like? Let's design and implement an example real-time data engineering pipeline in this chapter. The business scenario for the real-time example is website analytics. An enterprise runs an e-commerce website selling multiple items, like Amazon.com. This website is used across multiple countries. The enterprise wants to track visits to the website by its users. It wants to know about the visit date, country, and duration for which the user stayed in the website. It also wants to track the last action before the user exited out of the website. This last action may be in the catalog page, the FAQ page, the shopping cart, or the order fulfillment page. To enable this real-time analytics, we need to build a pipeline that will receive a stream of website visit records. For each user who visits this website, the stream will have one record. The record will contain the visit date, the last action performed by the user, the country from where the browser session was initiated, and the duration of the visit. Using this information, we need to compute the following in real time. We need to compute 5-second summaries by last action performed and write it to a database. We need to keep track of the number of visits by users by each country. We also need to What does the design for the real-time website analytics use case look like? We have an e-commerce application that is running in the cloud data center. The application creates user visit records when the user exits the application and publishes them to a Kafka queue called spark.streaming.websites.visits. It's possible that the application is located in multiple data centers across the globe. Even in such cases, the data is streamed into a single central Kafka queue. An Apache Spark job called Website Analytics runs and consumes the visit records in real time from the Kafka queue. On the data that is received, it will execute multiple actions. First, it computes 5-second summaries and inserts them into a MariaDB database called Website Stats. A table called Visit Stats is used to capture that information. Next, it maintains a running counter of the total duration by country using a Redis sorted set. Finally, it filters those visits which ended in the shopping cart and publishes them to the spark.streaming.carts.abandoned topic. This solution is natively scalable. Kafka provides scalable real-time streaming of data. Spark jobs can scale across multiple executors based on the incoming data load. Redis. To execute the website visits pipeline, we first need a streaming data source. Let's create an example data stream. The code for this chapter is available in the com.learning.sparkdataengineering.chapter4 package. The visits data generator is available in the website visits data generator.java file. We have already created the required MariaDB table and Kafka topics for this chapter when we ran the setup prerequisite script earlier in the course. In this Java file, we simulate a data stream and publish it into a Kafka topic. It implements the runnable interface and will be called from the main code to trigger simulation in real time. In the run method, we wait for 5 seconds to allow for the calling program to be set up. We then define various properties for the Kafka instance running in the Docker container we started earlier in the course. We define a sample list of countries and a list of last actions. We also create a random number generator. We then proceed to create 100 sample visit records. For each record, we pick a random country and last action from the predefined list. We also set the time to the current time. We set the duration to a random value. We form a JSON record for this visit with all the simulated attributes. Then we publish the data to the Kafka topic spark.streaming.website.visits. We then print the data published to the console. We will now proceed to create the main website analytics Spark job in the next video. Let's start building the streaming website analytics job now. The code for this is available in the streaming website analytics.java class. In this job, we first set up the Hadoop home directory property if it is a Windows-based system. Next, we need to set up a Redis writer client. The client is available in the rediswriter.java class. This is a simple client that connects to the Redis running in the Docker container we set up earlier in the course. It manages a sorted set called country stats. The setup method clears the key if it already exists. The open method opens a Redis connection. The process method increments the counter for the sorted set with a specific country as the key and duration as the value. We also have a MariaDB manager that manages connections to a MariaDB database. The MariaDB writer is used to write records to the database through the MariaDB manager. Now back to the main job. We initiate the website visits data generator in a separate thread and start the thread. This will start publishing visit data into the Kafka topic, which will immediately be consumed by the job. In the job, we define a schema for the visit record received through Kafka. Then we initiate a Spark session with local as the master. This runs an embedded Spark instance. We then proceed to subscribe and receive visit data from the Kafka topic. To extract relevant attributes from the Kafka record, we use the schema defined earlier and cast the values to specific columns. We print the schema received as well as the data received from the Spark data frame to the console. The first analysis we perform is to filter for records where the last action is shopping cart. We publish these records to a Kafka topic called spark.streaming.carts.abandoned. Here we first format the record into a CSV and then publish to Kafka. Next, we update Redis to maintain a running counter by country. The Redis writer class The real-time pipeline writes to three different destinations, namely Kafka, MariaDB, and Redis. We need to monitor these destinations to make sure that they are updated while the pipeline is running. For this purpose, we have some utility browser classes available. Let's start with them. We start with the shopping cart topic browser.java. This class listens on abandoned carts topic and prints the records as they are received. Let's execute this topic browser. It will wait until new messages are received. Next, we go to the country stats browser.java. This reads the sorted set from Redis and prints the duration every 5 seconds. Let's start this browser too. We then move on to the visit stats db browser.java. This class reads the visit stats table every 5 seconds and prints the total count and duration. Let's start this browser too. Finally, let's go back to the main program streaming website analytics.java. Let's run this code. We see the Kafka data generator generating sample records into Kafka topics. The records are being received and processed. Now we will look at the country stats browser. We see the counts being updated every 5 seconds. We move on to the visit stats browser. We see that the number of visit stats records are increasing also every 5 seconds. Note that there is a watermark set, so it will take some time before we start seeing records here. Finally, we look at the shopping cart topic browser. We see that the records for shopping carts are now available in this topic. When building an Apache Spark pipeline, would you choose a batch or a real-time pipeline? Data engineers and architects have a tendency to build all pipelines as real-time pipelines whenever possible. The key justification is that it is super fast, would generate the required insights instantly, and enable business actions. It is also considered cool in the data engineering world. But before jumping into building real-time pipelines, we need to understand the complexities involved. Real-time pipelines deal with unbounded data sets. This makes it difficult to size compute resources like memory and clusters. When doing time-based aggregations, we need to deal with windowing and watermarks. Irrespective of how delayed the watermarks are, we do end up with missed events and incorrect aggregations. Real-time state management is another challenge to ensure that state is properly maintained across the Spark cluster. Reprocessing of events is complex when issues happen. It is not a simple rerun of the job, but a number of items need to be reset, like checkpoints and state. So, when building a pipeline, it's important to analyze the requirements thoroughly before deciding if a real-time pipeline is appropriate for the use case. Go for real-time pipelines when responses, analytics, and actions are needed with latency of few seconds. Do make sure that this is a mandatory requirement, not a nice one to have. If this pipeline needs to process a continuous stream of real-time events, then real-time pipelines are a good choice. The processing should also involve minimal and mandatory aggregation and analytics. Adding too many aggregation steps will introduce complexity with watermarks and state management. When scaling a data engineering pipeline, all stages in the pipeline need to scale in order for the entire pipeline to scale. Extracting data and loading processed data into destinations are time consuming as they usually deal with disk reads and writes. How do we scale these steps when building pipelines with Apache Spark? Let's start with data extraction. Spark supports parallel extraction of data from various data sources. For example, Spark can read JDBC records in parallel across its executors. Similarly, it can divide up Kafka partitions between executors and process them in parallel. For the data source being used, analyze the out-of-the-box options provided by Spark for that data source. Exploit these options for parallel reads of data while maintaining data consistency. If possible, choose a source technology and build the source schema in such a way to suit parallel operations. This option is only available if the source systems are also being designed and built at the same time as the data engineering pipelines. Spark supports predicate pushdowns. This pushes down filtering operations to the data sources, so unwanted records are not read into memory. Leverage them when possible. When doing parallel extractions, build defenses against missed records and duplicate records to ensure accurate results. What about loading data after processing into data sinks? Each Spark executor can write independently and in parallel to a data sink for most out-of-the-box data sinks. Analyze how Spark works with a specific data sync technology like RDBMS or a Kafka queue. Understand the impact of record additions and updates on trans. How can we scale processing of data with Apache Spark? Apache Spark is built for massive distributed operations, but care should be taken during pipeline design to avoid choke points and shuffles between executors. Filter any unwanted data as early as possible in the pipeline. This reduces the amount of data kept in memory and moved around executors. Minimize reduced operations and associated shuffling early in the pipeline. If needed, move them to the end of the pipeline as much as possible. Repartition data as needed to reduce the number of partitions. Certain operations have the tendency to create too many RDDs, so keep track of this. Cache results in the pipeline when appropriate to reduce reprocessing of data. Avoid actions that send back data to the driver program until the end. This minimizes shuffles between executors. When we build scalable data pipelines, we also need to build resilience into them to make sure that the pipelines can support critical operations and deliver reliable outcomes. Apache Spark provides various resilience capabilities out of the box against failures. It handles failures at a task level, stage level, and executor level. That is an important reason to use Apache Spark. However, some additional considerations are required to make the solution resilient. Monitor Spark jobs and Spark clusters for unhandled failures. Create alerting systems by which required personnel are informed and problems can be fixed quickly. Use checkpoints for streaming jobs with persistent data stores. Even if Spark restarts, it can resume from where it left off. Build resilience in associated input stores and output sinks. After all, it's not enough for Spark jobs to be resilient, but the entire solution should be. Choose data stores that provide redundancy and having learned about data engineering with Apache Spark, let's implement them in an end-to-end project. This is an exercise for the students to try out by themselves and then refer to the solutions provided in the chapter. There are always multiple ways to achieve the same end result. The solution provided in this chapter is only one such possible result. Here is the problem statement for the exercise. In Chapter 4, Streaming Use Case, we created a MariaDB table with 5-second summaries of the last action performed by website users. We are going to use this table as the input and then build a downstream pipeline to analyze significant actions and maintain a running count table of the significant actions. Please refer to the setup prerequisites.java class in the setup package of the Java project if you need to understand the schema of the visit stats table. Let's review the detailed requirements for the exercise. The task is to run a job every day and extract last action records with a total duration of more than 15 seconds within a 5-second window. Do make sure that you have executed the examples in Chapter 4 so there is already data available in this table. Next, stream these significant last actions to a real-time Kafka topic. A topic called spark.exercise.lastaction.log has already been created for you during the setup process for the course. Then, analyze the significant actions in the Kafka topic in real time and maintain a running counter of the significant last actions by action name. This use case combines a batch processing task and a real-time processing task and is an example of an hybrid pipeline. The example itself is naive but will demonstrate the use of the techniques learned in the course. Best of luck for the exercise. Please refer to the rest of the videos in this chapter after you have completed this exercise. What would the hybrid pipeline for the course project look like? We start off with the MariaDB table called visit stats in the website stats database. We first build a long last action extraction job. Actions with long durations are considered significant actions. This job will filter records from the database and extract those with a duration of greater than 15 seconds. Each of these records will be published to the Kafka topic. Let us examine the example code for the first part of the exercise, extracting long last actions. The code for this example is available in the com.learning.spark.data-engineering.chapter6 package. The file is long last action extractor job.java. Please note that the original records were generated using system date when the website visits data generator was run. So use the right date ranges. First, we need to extract the records from the MariaDB table. In order to take advantage of parallelism, we first find the min and max bounds for the records using the bounds query. Then we define a Spark session. We execute the query to filter for long actions and store them in the last action dataset. We take advantage of parallelism by setting the relevant options for bounds and partitions. Next, we extract the last action column from the dataset and publish it to the Kafka topic spark.exercise.lastaction.long. Finally, we print the total number of records that were fetched and published through the job. Let's run this code and review the results. We see Let's build a running scorecard for long last actions published to Kafka in the previous video. The code for this is available in the scorecard for last action job.java in the chapter 6 package. To help with managing the Redis sorted set, we have the Redis writer class. This Redis writer maintains a sorted list called last action stats on the Redis instance running on Docker. It has functions to maintain the sorted set. Here, it increments by 1 every time a last action occurs in the data stream. Back to the main job scorecard for last action, we first define a Spark session for the job. Since we only have one value in the topic, last action, we don't need to define a schema. We read the topic directly into the raw last action dataset. From there, we extract the value as last action into the last action dataset. We print the schema and we also print the contents to the console. To maintain the Redis sorted set, we use the writeStream method and call the Redis writer for each record. This will update and maintain the Redis sorted set. We will use the countdown latch to keep the job running. In order to review the values in the sorted set, we also have a last action stats browser. Let's first start the browser. Now let's run the scorecard for last action job. We also need to run the long last action extractor job in order to generate new records, as the scorecard for last action job only listens for new records. Now that you have learned about how to build data engineering use cases with Apache Spark, you can take your learning even further. First, learn more about batch and stream processing use cases with Apache Spark with other courses in this platform. Second, learn about how to use similar technologies like Kafka Streams and Apache Flink for the same use cases. And finally, solve a new data engineering problem in your organization using the learnings from this course. Data always intrigues me. I bet it intrigues you too. So let's keep exploring it and find better ways of extracting knowledge out of it.